Okay, the second thing you need to consider is we call the selective oxidation. The selective oxidation means we want to oxidize only a portion area, not the whole area of the surface. So in this case, we will first deposit some kind of protection material, for example, like silicon nitride on the surface, to prevent the diffusion of the oxygen onto the bottom surface. We leave only the center part for oxidation. However, consider when we do the oxidation, if you want to grow 1 micron silicon dioxide, okay, in order you will take only 0.44 micron silicon. So that means the original surface will be extruded out of the surface because it becomes thicker. You cannot go down, right? So the only way is to go up. So it will grow thicker and extrude out. So in out, you got the extrusion type of things, the mesa type of things of the structure on the surface. The surface become not flat. Sometimes it's not good for making like sensors. Some sensors we like the surface is extremely flat, like an accelerometer, like some kind of a pressure sensor. We don't want extrusion. So in this case, we need to consider to take out some material first. For example, we want to grow 1 micron. We take out 0.56 micron of silicon first. We use the bottom 0.44 micron silicon as the base for growth. So in out, after the growth expand to the top by 0.56 micron, you got the flat surface on the top. Okay, because originally take out 0.56 micron. So you grow back the 0.56 micron. The surface become flat. Okay, but still have some burst space on the side because some oxygen diffuse to the side. So sometimes we got some extrusion on the side. But if you this area is pretty large, this side effect is not very significant actually. Okay, it's a schematic, so it draw, yeah, like a cartoon. So it looks more serious, but it's okay actually. Only a little burst big. Okay, so for different oxide thickness, you already got the color, so you can take a look. Color is like cycling from red, brown, and also yellow, and also blue, purple, and come back again. So it's like a circling sense. So according to the color, after deposition of the growth of the thermal oxide, you can see what kind of thickness they are according to this table. Okay, it's for your reference. Okay. So now we finished the first part of our IC process. Any question regarding this lecture? The 3-1. I think it's very straightforward. Okay, so you can go through all the detail later on. Okay, if no further question, we need to go on to the next part. Okay, the 3-2. Hopefully you can finish 3-2 today, but not easy because we got a lot of material here. So maybe we'll remain like half of the material to the next week for more detailed discussion. So we will try to finish as many as possible today. Okay. So now go on the second part of IC purification, the diffusion, implantation, film deposition, interconnection, and contacts. Those are practical things. Okay. So after we understand the oxidation process is part of a diffusion process, then we go to the second consideration, diffusion process. The diffusion process is not talking about the oxidation process. We are talking about we want to introduce impurity into the silicon wafer to change the electricity, the electric conductivity of the silicon substrate. So this process is important to form the drain and the source. Okay. So when we deposit high concentration desired impurity onto the silicon substrate surface, so there are several modes to drive the atom into the silicon lattice to make the silicon more conductive. Okay, so basically there are at least two mechanisms. The first one we call the substitutional impurity, substitutional replacement. For example, originally you have a silicon lattice like this, single crystal silicon, but some defects here, the vacancy, So here we are lacking one atom for silicon. So now you introduce another impurity, for example, like phosphorus, into this area. So the boron will replace to go to the vacancy to replace the original position of one silicon. So this process we call the substitutional impurity process. Okay, substitutional process. But substitution process is kind of rare because you don't have many vacancy actually, really inside the silicon substrate, not many defects. And so we need to consider the other mechanism. The other mechanism is the impurity will go through the inter-atom space. Okay. Then try to find a time at a higher temperature to replace the silicon atom. So this process needs energy actually. It will not happen naturally. So you need to give up some temperature to have give higher temperature, like more than 600 degrees C, even to 1000 degrees C. So in this case, the impurity has the ability, has the chance to replace the silicon. So in this case, the impurity can contribute his electrons for conduction. Okay. So when those impurity only diffuse between the atoms without replace the silicon atoms, it has no function actually. It has no ability to contribute electrons as a whole. Okay. So for those impurity, need to has a functionality to contribute all our electron. You need to find to either replace the silicon, place or occupy a vacancy. Okay. That means you need to go to the lattice. Okay, become part of the lattice. If only stayed between the atoms outside the lattice, it's no function for the impurity. So that's why for all the diffusion process, we usually will go through two steps. The first step, we try to introduce atom into the substrate. And the second one, we need to use a different temperature to increase the energy of the impurity to replace the original silicon atom, okay, to make it functional. So the second we call the driving process, okay. So there's a mechanism for diffusion. So the mathematical model for diffusion is a fixed first law and second law. I think it's a textbook things, so you can revisit easily. So that means for the first law, we just mentioned first law, the flux of your impurity will be proportional to your concentration gradient, okay, and also your diffusivity. These two products together. And for the second law, when you have some kind of a control volume inside the control volume, if you have like a numbers of your impurity increase inside the control volume according to time, that means those impurity are flux from the boundary into the center part, into the control volume part. Okay, so the flux will be generated, the driving force will be generated by the flux gradient. You have flux gradient from the boundary go into the center part. So this is a continuity equation. So we combine these two together, we got the fixed second law. Okay, the fixed second law is a PDE, partial differential equation. So you need to solve it by using a spatial way. At the solve this equation, you got a result. So don't worry about the solving the equation. You just need to understand the final result, the physical meaning. So we got two different kind of function according to different kind of initial condition or boundary condition. So here we look into the figure, will be easier to explain. So we got a two boundary condition. The first one we call the constant source, okay, condition. Constant source condition means we provide the impurity on outside surface with a fixed constant concentration all the time without change. So that means you will see the concentration of the impurity on the surface will be a fixed number. We call it N0, okay? Will change with time. So all the time, it keeps the same constant. And as time advancing, so you can see the profile. This called this is the profile of the impurity inside the silicon wafer from zero deep into your silicon surface substrate. So at the time, you can see the profile is quite steep. And as the time progressing, you can see the impurity will go further into the depth of your thickness of the silicon substrate. So as the time approaching, you can become more and more area has been diffused by using the impurity. Okay, so this function is an arrow function type things. So the total impurity you introduce into the substrate will be the area, the area under this curve. So as time approaching, you got the more and more atoms diffused into the substrate. But the distribution will be different. You have a high concentration on the surface. The concentration is fixed as N0 because you fix the outside environment. And you have a lower concentration at a deeper area, a deeper surface, okay, inside your silicon substrate. So these are the first type things. And if you change the boundary condition into the second boundary condition, we call the limited source diffusion. That means we introduce only a fixed amount of impurity into your substrate. After that, the surface live into the ambient without any kind of a source. So the source is limited. The source is the things you originally take that amount. They don't add more. So you can see the concentration on the surface will keep reducing, right? Because as time approaching, the impurity will go deeper into the substrate. It penetrates into the deeper area. Okay. However, the surface concentration will be reduced because you have a limited source of diffusion. So the bottom area, the area under the curve, will be the same. That means the total amount of impurity introduced to the substrate will be the same. You have that amount. As time advancing, you got a different distribution. Originally, you have a very steep distribution. As time progressing, you got a more slow, is not that steep distribution. So the concentration on the surface become lower and lower, but the penetration become deeper and deeper. But the total amount will be the same. So this second type we call the limited source diffusion. Actually, all the fabrication process will go through these two processes. So we use the first process to introduce certain amount of impurity we want. After that, we bring the substrate into a furnace without any source. Just elevate the temperature for annealing process. Try to distribute the impurity into the profile we want. Okay, so two-step process usually we will use for the diffusion. So the second model, by using the limited source model, the boundary condition, the N-out equation solved from PDE will become a Gaussian distribution. So this is a Gaussian distribution, exponential type things. Gaussian distribution profile be a little bit different from previous one. It's an arrow function. Okay. Okay, so yeah, here we have a two-step diffusion. The first step diffusion we call the pre-deposition step. The pre-deposition step usually we will bring the wafer to in contact with a fixed amount, not fixed amount, fixed concentration of the source, impurity source. So we allow certain amount of the impurity go into the substrate. Then we will go to the second drive-in process. The drive-in process has two purposes. The first one, we want to redistribute the concentration into the beta profile because we want the profile become more uniform. Okay, inside the silicon substrate. That's the first thing. The second thing is that remember, for the diffusion process, you want to make the impurity really working for you. You need to consider these two mechanism. The impurity need to replace the position of silicon. Otherwise, it cannot work properly. So the driving also gives the ability and the energy to allow the impurity to replace the silicon. Okay. Okay. To perform original design impurity functionality. Okay. So that's why we usually using two-step diffusion process. Okay. If you have a successive diffusion, okay, actually the DT product will be the summation of all the DT products together. You will get the final profile as a whole. Okay. When you plug this value back into the equation. Okay. So you can diffuse several times, but the final results will be the DT product, the final value plugged into the equation. You can find out. Okay, after diffusion, sometimes we need to find out what's the depth of the diffusion. How deep you diffuse the things into the substrate. So we need to using a very special tools method to do the estimation. Because the thickness is usually very thin, it's only like a couple hundred nanometer or even shallower. So it's not easy to do direct measurement of the thickness of the diffusion. So usually we were using the way, okay, by using a wheel to cut the surface into this kind of circular shape. So in this circular shape, we will change the thickness into the length here. So length will expand the thickness, and you can visualize this length from the microscope. From the length, you can using the equation down here to calculate the thickness. Because of the length, because is a slope here, so the length will be much larger than your thickness. So it will, for example, you have a thickness around like 500 nanometer, but the length can be couple micron. So the couple micron will be easier to be measured under microscope. So the measurement will be more accurate than you directly measure the thickness of the diffusion layer. Okay, so the equation is like this. So the thickness Xj, okay, so will become, because the radius will be r, okay, using the wheel to cut the surface, the radius will be r, and then from the center of your the wheel to the top of the substrate will be x, and the thickness will be xj. That's the things we want to measure. So x plus xj is this kind of, if you consider the right triangle of this one, okay, so x plus xj will be r. R is from here to here, r squared minus this part called b squared, and put the square root. Okay, so this is for the whole length here. And for the length of x, you can consider another rectangle, rectangle like this one. So the x will be the r squared minus a squared. A is the length of here, and then take a square root. So if you using the first one minus the second one, you got the thickness of xj. Okay, so after some rearrangement equation, you end out the approximation of xj equal to this equation. So this equation tell you we can do the measurement of A and B. A means the center, the length of the center part to the border part of your cutting, and the B means the bottom part from your center part to the border of your cutting. Okay, so the difference will be the dominant things. So xj will proportional to your A minus B here. Okay. Yeah. So this is the easiest way to do the measurement for the thickness of a diffusion. Okay, then we will consider another important parameter we call the sheet resistance. Usually, sometimes we use it inside the IC process. So after diffusion, the surface area become conductive. So we want to measure the resistivity or resistance of that. So the measurement will be by using the 4-point probe method. We introduce the 4-point probe first. The 4-point probe method is by using 4 different probes, using the outer 2 probes to provide a fixed current through this region. Use the center 2 to measure the voltage. Okay, why are we doing this? Maybe you will ask this question. Why not use only 2 probes to measure the resistance directly? The problem is when using only 2 probes to do the measurement, okay, you measure the resistance not only on the substrate, but also include the contact resistance of your probe to the substrate. And you don't know the number of contact resistance and also the substrate resistance as well. So you have 2 variables, but you have only 1 equation. You cannot solve that. Okay, so that's a problem. So to prevent this kind of situation, to take out the interference of the contact resistance, so now we have 4 probes contact with the surface. So all the surface have contact resistance, but we give it a real current. So we know the current, and we measure the voltage. So the current or the voltage are the real measurement, and we plug into the equation. The equation is found. You need to integrate the current and also those kind of things to become potential. And finally, we got these 2 equations. When the thickness is pretty thin, more like compared to your the distance of your 4 probe, the probe distance is around like a millimeter, a couple millimeter to centimeter range. So, for example, you have only like a 500 millimeters thickness. It's pretty thin compared to as the probe distance. You can use plug into the second equation. The second equation, the resistivity will be some kind of parameter times your voltage over your current. Okay? However, you have like a thick substrate. For example, like a thick substrate, you want to measure the total resistivity of thick substrate, 500 micron. So 500 micron is similar to your probe distance. In this case, you need to plug the first equation, okay, to get the resistivity. So so after your measurement of resistivity, okay, now we come back to the resistance. Okay, so the resistance of a wire, okay, will be proportional to a resistivity times the length of the resistance, and divide by the cross section of the resistance. So you have a longer line, you have a larger resistance, you have a larger cross area, so you have a smaller resistance. Okay, there's a typical rule, and also depends on the material used. The material or different material give different resistivity though here. But in IC industry, sometimes the thickness of the resistance is fixed because you go through the same process. You deposit the metal fin at the same time. So everybody's thickness is the same. So that's why we are used to put the thickness together with the resistivity together to form a new parameter. So the new parameter we call the RS, we call the sheet resistance. Okay. So the sheet resistance means you need only to times the total resistance. Okay. Once we give the value of sheet resistance, when you see a line, how do you calculate the resistance? The calculation becomes very easy because you need to count only the ratio between the length and the width. Okay, the length and the width. When you're using the length to divide it by the width, that means it become you can consider that there are many squares connected to each other. Each square have the same width on this side and on the other side. Okay. So you count the number of the squares times your sheet resistance, you get your final result of your total resistance. Okay, now easy to understand. For example, you have a line, okay? After deposition, I give a sheet resistance, RS. You can get this easily from your IC fabrication process. You send out your substrate to TSMC, for example, for fabrication. So here will give you this number. He's not giving you the resistivity. Instead he gives this number. So this number is a combination of resistivity and also thickness together. So when you bring the wafer back, you don't need to consider back the resistivity to calculate the resistance. You can use this directly. Remember, the total R equal to RS times your length over your width, right? So for example, you have a wire like a L long and W in width. Okay, L divided W, that means you calculate how many squares over here. Each square is a W times W square, okay? Here is a W, and here is W as well. That means 1 square, okay? So you calculate the number of squares. The number, so this value becomes a number. How many squares you have? So using the number times the shear resistance, you can get a final resistance very easily. You understand? Okay. So foundry only give you this number, and for you, your design is easy. You just measure how many squares you have. So this kind of things can make you very simple idea. So you have a thinner one, okay? This is length 1 with 1. This is length 2 with 2. But if your number is the same, you have got the same resistance. Because they share the same shear resistance. You have a thicker wire, a thinner wire. If your length width ratio are the same, they have exactly the same resistance. Yeah, for example, the numbers of squares. They have the same numbers of squares, that means. So these have smaller squares, larger squares, but they have the same final resistance. If they have the same numbers of the squares on the wire. Okay, 好。So this equation is for straight line, straight wire. But sometimes you have some connection, or you have a wire have some bending. Okay, from one side bend to different direction. So in this case, for the squares on the border, on the connection area will be a little bit different. Yeah, because the model is not the same as the one we mentioned. So in this case, you need to consider differently. For example, the corner one. For example, you have a bending from horizontal direction down to the vertical direction. So for the connection part, this one, the resistivity or shear resistance will be a little bit lower because the current path here is shorter. Consider, yeah, current path is shorter here, so you get the lower resistivity. Lower shear resistance for this square. So when you add them together, this part need to be considered only 0.56, less than 1. Okay? And then you have some connection like this, from the top to the bottom. Bottom you have a large square, but the contact window only a small portion here. Because you have a current from the restricted area and expand to the larger area. So also you have a smaller with shear resistance for this kind of connection from top to the bottom. For this one, 0.65 for this one. Okay, this is another one. Not only the contact area become large, but also the connection one become very large. So you have a contact here is even with smaller contact resistance, 0.14. Okay. Yeah, this is another one. So just give some example. Yeah. Only for those are special case. Okay, when you do the connection, do the bending or doing different things, you got a different value. But most of the time we use this equation in very simple way. Just count the numbers of square. You got the final results of resistance. Okay? Okay, we stop here, take a break, and we come back later. Thank you.